I have two of these Hewlett-Packard 3455 digital voltmeters and also two 3456 digital voltmeters, which are a little bit newer than this one. Three of them work now that I repaired one of the 56s in the last video, but this one didn't work. I got it for dirt cheap, like 20 bucks, because it didn't work. And I've done a tear down of this and a quick look around inside, because the seller said that morning he turned it on and smoke came out of it, and I can't find anything inside of it that looks cooked, but maybe I have to have a closer look. But I'm looking at this now because after the previous video where I found a faulty capacitor, this guy, in one of the 3456s, I thought I should replace the capacitors in all four machines. And right there we can see a very similar capacitor. In fact, it's a different capacitance, 7500 versus 4000 microfarads, but it does exactly the same job. It's the filter capacitor for the outguard plus 5 volt supply. Now, what I didn't do when I tested it briefly in the original teardown was just looked at the voltages with a multimeter, and they seemed okay. I found this one by faulting this one by looking at the output of the 5 volt rail with an oscilloscope, and you could see massive ripple like this. Looks like our 5 volt power supply for the in-guard is cactus, which was caused because this thing had gone open circuit. Now, I wish I'd tried to measure that 5 volt rail with a multimeter to see what it said. I expect it would show less than 5 volts, but would it have shown 3.75? Yeah. It would have shown a bad voltage, I'm sure. Maybe all these are pretty good because none of them appeared bad with a multimeter, but I'm going to go over them with an oscilloscope this time. So we'll do that. The fault, if I turn it on, this has a fan that the other ones don't have. There's this overload coming on. And there's a test function which comes up with 11. It's testing auto cal constants. The manual's not very clear on it, but every time you press it, it counts down. It doesn't show 7 or 4, and then it goes to that. Press it again, we get 11. So I don't know if that's a whole series of faults or what, but first thing you have to do, no matter what, is check the power supplies. So we'll do that. Now, I've verified that on the outguard the 0 volts is connected to the frame, so I can use the frame as my ground point for the oscilloscope. And in the in-guard, when the guard switch is pressed in, guard is connected to low, so I can use the in-guard frame as ground for the oscilloscope as well. We're currently looking at the plus 5 volt test point there, and we'll turn on, 1 volt per division, 5 volts, looks pretty steady. So yeah, 5 volts looks pretty good on the outguard. Now we'll check the in-guard voltages, and the in-guard frame is ground, plus 5 on the in-guard, also looks pretty good, plus 9, going down to 2 volts per division, plus 9 is 9.5, 9.6, probably good, looks pretty straight. Next, put this up in the centre, 5 volts per division, minus 15, that looks pretty good, minus 15.2, plus 15, also good, minus 24, good, and plus 30, also good. Yeah, so all the supplies are good in this. Now the next step, according to the service manual, is to do a technique called half splitting. And to do that you need a working 3455, which luckily I have. And what you do is, I'll just move this board, this is the outguard CPU board. Makes it a bit easier to get to this. Not a lot easier, but yeah, that plug which connects the outguard to the in-guard, that goes straight to a pair of opto couplers on the in-guard board. What you do is you get a cable a Hewlett-Packard service cable, but I can make one pretty easily. It's just 8 connectors, or 8-pin connector with one of them blocked off. You connect that on one machine to this on the other, and that way you're using the out guard from one and the in guard from another, and see where the fault goes, if it's still in one machine or it goes to the other. By that means you can determine whether the in guard or the out guard is failing, and because the troubleshooting steps require you to know which part is no good. Next thing I have to do is make up a little cable to do that. Right, here we have the two 3455s, the one that works. Good meter. And the one that doesn't. Bad meter. And I've made myself a little service cable to do the half split bizzo. A bit rough, isn't it? But hopefully it works. So to verify that, I'm going to put it in the good meter, make sure that the good meter stays good with this. So I'll do that. Turn that off. Power switch on this has got a bit dicky. Right, there's my service cable, and if that's good, this meter should still work. I can't see anything wrong with the cable. No. Alright, so that's good. Now we'll try half splitting. In the bad unit I suspect it's going to be the in guard that's no good. So we'll test that first. We'll use the out guard from him and the in guard from this one. So to do that, the socket of this goes to the pins on the out guard board, so we're using the out guard. And then at this end, we plug it to the in guard cable. So we're using the in guard on this guy. And they say you turn on the one with the active in guard first, which is this one. So this one's now working. So the problem is something in its in guard. Just to verify, I'll swap them over. Right, now I've got this going to the out guard on that one and to the in guard on this one. So now we turn this one on first, and this one should now do that OL, overload. So confirmed. Problem is in the in guard area. Another thing we can do is try swapping the ADC board and or the AC, the RMS board. Still getting our overload, which indicates that it's something on that motherboard of the in guard, not the ADC converter and not the AC converter. There's still the ohms converter up there, and below that is the reference. And one thing I didn't check before is the voltage coming out of the reference, so I should probably do that. It should be plus and minus 10 volts. I'll just do that. Right, now that we've used the half split method to make sure that it's the in guard section of this that's at fault, I can probably stop using the service cable and the second meter. I'll put the plugs back in. Let's just make sure this still works. Good stuff. And this one still is his problem. Yep. All the other boards are back to where they belong. Now this OL indicator on startup steers us to service group B, which is a lot of things to test, and the half split procedure that revealed that the in-guard board has a problem sends us to service group E. And both of these say to check the reference voltages, plus and minus 10, coming from the reference module, which somehow snakes its way all over the board to here. And I've done that and I didn't like what I saw. Now there's the plus 10. As you can see, it's not steady, and it's 7.4 volts. It's jumping up and down, and the minus 10 is no better. Same thing at minus 10. The reference assembly is down there. It's an unpluggable module. In fact, you can calibrate this thing by unplugging that module, sending it off to get calibrated, and then you just put it back in and the thing's calibrated. That only goes, as far as I can tell from the schematics and block diagrams, is it only goes to an op amp down here where the test points were, and then which takes +10 and inverts it to produce the -10 as well. They only go into the ADC board, and previously we seemed to get the idea that the ADC board was good. I might just try pulling that out just to see if that might be loading down those voltages, and if not, we'll have to have a look at the reference assembly. So I'll turn this off, take out the ADC, well, it is steadier, although it's still the wrong voltage, -7, and we try the +10, still 7.6. Not jumping around as much as it was before, but the voltage is wrong. So that means looking at the reference assembly, I think. And the reference lives behind this little gate, and that sticker was intact. I've already had it out, have a look inside, but yeah, it hasn't been fooled around with since when this thing worked. And behind that there's a little bracket bar that holds the reference in, and then we can pull the reference out. Cute little module. And I'll wire some power onto this and see what voltages come out of it. Right, there's the reference assembly, ground and the 10 volts output are there, and I've connected 4 wires for power. And if we look at the schematic, there's actually 2 sections in there. There's a precision resistor section for the ohms measurements, but the part we're interested in is this, which uses a ovenized Zener diode. It's not an LM399, it's some weirdo Hewlett-Packard number, so if that's buggered, it's going to be hard to replace. So we need plus 29.3 volts for the heater, uses -15, so there and there, and grounds are here. There's also another ground which this appears to use, ground R, so I'll connect those 2 grounds together, which is those 2, and we're looking at the output voltage on the good HP3455, and connect the -15 first, and then the heater power, and we get 3.2 something, and look at that, 10 point not much, so I guess that's a relief. The reference works, so there's something on the motherboard that's screwing up the reference voltages, and it can't be much. It goes to this inverter and then to the A to D, and these are the 2 points we measured before, which were wobbling and only 7.6, so it looks like when we disconnected that and they were still bad, although they weren't jumping as much, they were still about 7 volts though, so it looks like there's something wrong around there. Hopefully that's easily fixed. I'll put the reference in a bit of a thermal insulation to try and let it stabilise, and it's been running for many hours, and it's drifted down. It seems to have levelled off at 9.9997 volts. Right, the 10 volts reference module's been reinstalled. We're looking at test point 8, which is its output, should be plus 10 volts. And we verified that it is coming out of the module as 10 volts when it's standalone. Turning on the power, and we see it's still being held down by something. We've shown that it wasn't the ADC board. I looked at that because this block diagram, the block diagram shows that the reference goes to an inverter, and there's test point 8 that we're looking at, and only goes into the ADC, and of course that's not correct. I knew there was something wrong about that because it doesn't work like that in the 3456. The reference also goes into the switching network. So if we look at, there's the reference module, there's the inverter, test point 8, and yeah, there's these other connections shown there, and they are all inside the input switching section, which is this. I don't know if the highlights show up there, but they're all associated with FETs. This is a bit hard to read, so I'll split it up into smaller, easier to see pictures, and here's 3 of those points that it goes to, and the other 3. Now, going into 510k, well, that can't possibly be pulling it down, although there it could. If that FET was on and low, that would drag it down. Up here we've got 100k, also couldn't be pulling it down, and here 510k couldn't pull it down, but again, directly connected to these 2 FETs, either of those could be pulling it down. There's a diode there, but unless that's shorted, it couldn't be pulling it down. It can only pull it up. So let's look at test point 4, see if that's much lower than 10 volts, and the other side of that FET, which is here, and it joins to this FET, which goes to ground. So if those FETs are both on, it'll be pulling it down also. So I'll get to those test points and have a look. We'll do this one first. The other side of those 2 FETs is here. One of them goes to R47, which is what we're monitoring there, and turning it on. That seems to be about the same voltage as the reference. So it does seem to go to 0. I'm not sure what to make of that. Let's have a look at the other point. The other side of those FETs, which is test point 2. It's also bouncing around like the reference voltage, but doesn't seem to be going to ground like the other one does. I'm not 100% sure. I'm not at all sure what to make of that. I was hoping to get a shortcut by just looking to see what was dragging down the reference, but so we'll look at service group B. And looking at this table in service group B, cal constants failed, and there's no combination there that matches what I'm getting, which is 11 through to 0 failing, except 7 and 4. There's not that pattern there. There is 7 and 4 by themselves. A few pages on, because I feel there's a shorted FET loading down the reference voltage, various other malfunctions, shorted FETs, blah blah blah. There's this measure gate to on resistance. I know what the gate is, but what's the on? Not sure what that means. There's this bizzo where you can step through a bunch of functions, but this one struck me. Shorted FETs and U1 may show up as an OL indication, which is what we're getting. This condition can be checked by measuring the voltages at TP4. If the voltage reads approximately plus 16 or minus 16, then measure TP3. If TP3 appears to be floating or is at minus 24, short the multiplex node to ground. And after a bit of buggerising around, I discovered what the multiplex node is. It's this along here, going from R38 through to the sources of Q1, 2, 3 and 4. And in the machine, the multiplex node is these 4 here. Q1, 2, 3, 4, and this is the sources of them going to R38. They're all sitting on Teflon standoffs. So that is the multiplex node. So I'll do what that procedure says and see if I can find anything. Now, I couldn't get any sense out of it using the multimeter, so this is looking at test point 4 on the oscilloscope, and that's all over the place too. Anyway, yeah, nothing convincing there. Well, yeah, so there are a few other approaches. The flow charts, there's one of these for each of the test error codes you can get from 11 through to 0. I started looking at 11. The voltage is always a little bit slightly different to what the levels they were giving suggested, and I thought I wasn't happy with that either. So there's this, which is a list of in each of the different faults, calibration states, what voltages you should see on the outputs and inputs of all these comparators that do the control of the FETs. Trouble is, the manual actually says that you have to do all this not in test mode, which is the only way I've been able to see these, to get it into these given states. They give a procedure for doing it without going into test mode, but I couldn't get it to work, and it doesn't work on my good 3455 either. So I posed a question on the EV blog about how to get it into those states without using test mode, and although I didn't get an answer to that, One of the responses indicated that I didn't quite understand how all this bizzo works, especially how JFETs work. Yeah, I just haven't had much to do with them apart from replacing a couple, but I haven't had to properly understand how they work. So I was labouring under a misconception. I'll explain that in a minute. But I also looked at a thread in the EV blog trying to fix one of these for someone. There was a few commenters saying try this, try that. And one of the things that they tried was to, like before, one of the earlier steps suggested grounding this multiplex node. Doing it in test mode was interesting. Turn it on, put it in test mode, and we get error 11. And if I ground the multiplex node while it's in error code 7, it goes to error code 10. And that is something to do with, I believe, Q2 not pulling the multiplex node to ground. I'm not sure how I can pull it to ground through 100k. This must be such a high impedance node that even 100k to 10 ohms is sufficient to pull that to ground. The other thing is I'm getting 2 to 3 volts on the multiplex node with the input shorted, even on just testing volts with auto cal off. So I'm a bit confused. I'm very confused, but I'm not happy that there's this 3 volts sitting there, 2 or 3 volts sitting on the multiplex node, and I think it should be 0. And I'm not happy obviously about the voltage ref being pulled down from 10 volts to 7 volts. So yeah, clearly I am stumbling about, going off in different directions and not really going very far before I get annoyed with that approach and try something else. And my latest approach is to look at the voltages on these comparators and see if they seem to be doing the right job. And I got sick of looking at flipping through pages of this thing, so I've made a very large format of it, which is easy to see everything at once. And yeah, now my issue that I mentioned before about not understanding how FETs work, I always just thought they were like little MOSFETs where they're off until you turn them on, but JFETs are almost invariably depletion mode devices, which means they're on unless you turn them off. So the drain and source are connected together unless the gate is pulled a few volts negative relative to the source. The other curious thing about JFETs is that source and drain are more or less interchangeable. So a bit strange like that. And I saw a video about all this, which I just saw again the other day, and I realised, I have seen it before, but I forgot all that. Now my misunderstanding was because of that. And another thing that's not very obvious from this diagram is that these comparators, they take inputs, these nodes here, all come from the processor, the digital part of the in-guard section, so they're logic levels, and this common rail here is at 1.2 volts set by these 2 resistors. So you'd think that the power supply to this comparator was plus 5 volts and ground, but it's not. The plus 5 volts goes to its VCC, but its ground pin doesn't go to 0 volts, it goes to minus 24 volts. And that's how it switches these FETs off, by pulling the gate down to minus 24 volts, which is sufficiently negative relative to whatever might be on the source or the drain. That FET gets switched off. So I went through and measured voltages on the outputs of all these comparators and what going into it. Now the comparators are LM339, I think, or 393. One of them's a dual, one of them's a quad, but it's the quad version, and it's an open collector output. So when the open collector output transistor is pulled low, is turned on, it pulls the output low, and when the output transistor is off, then presumably something pulls the collector high, some pull-up resistor, and that happens, it goes high, the transistor is off, when the positive input voltage is higher than the negative input voltage. So let's see if that's what all these things are doing. So for instance this one here, and I've measured all these voltages with shorted inputs, 10 volt range, auto cal switched off. So the auto cal makes stuff jump around all over the place, so things are steady when you have auto cal off. So this one for instance, the positive is 1.19, the input is a logic 0, so that is higher than that, therefore the output of this is high, or the output transistor is turned off, so it just floats up to whatever is connected to that, which is 7-ish volts, because that's all connected to the voltage reference via this resistor here. I'll look for all the rest and see if I can find any anomalies, but one thing I found is the inputs are either 0 volts or something like 4.4, that's a logic 1, but here on this one the input is 2.9, which is a pretty crappy logic 1. We'll look at that in a minute. But yeah, I'll check the output voltages match what the inputs say it should be. Okay, I found some interesting things. If you look for instance at this one, the positive input is 0 volts, which is less than the 1.2 on this rail coming from the voltage divider. So the output should be low, but it's not. The output transistor is not turned on, so it's allowed to float up. Here's the same situation, 0 volts going into the plus input, the negative input on the rail, and the output is low, minus 24 volts, so that's how it should be. So there's something wrong with that one. Similarly here, 0 volts into the plus input, not minus 24 on the output. Over here there's another one, 0 volts on the plus input, and not getting minus 24 on the output. And those three are all in U9. Now there's this other one that doesn't seem right, the bad logic level. Should be more than 4 volts or 0 volts, and it's 2.9, it's a bit sus, but that's on U4. And if we look just where that goes, another expanded diagram, it's this pin here, sorry that one there, there's the 2.9 volts, and the output from the latch that powers it is 3.5. These others are all zero, so there's nothing to compare it with, but 3.5 volts is not a good logic output. Now could this be pulling it low? Maybe, but 3.5 to 2.9 gives 0.6 volts, which is a drop across that diode. These two diodes, by the way, and that resistor are an afterthought. They only appear on above a certain serial number. It looks like some sort of a wired OR function was required there, and they added it with the diodes rather than redesigning all the circuitry or adding a gate. Maybe they didn't have any spare gates. So yeah, that is suspect as well. So I'm suspecting now U9, this comparator, perhaps U4 could be pulling this down, or perhaps U13 is a bit dodgy. So I've got spares for all those. That's a 74174, and the others are LM393s or 339s, whichever it is. So I think I'll first of all replace U9, see what that does, and then possibly U4 and U13. Right, there's the replaced U9 in the socket, and I guess now we turn it on. Just before I do, that's a quad comparator, remember, and we only found U9 in 3 places up there. I was wondering if the 4th one was used, and it turns out it's on this page with the in-guard processor and over there, and I didn't test that, so, but 3 out of 4 were bad, certainly. Okay, dare we turn it on? Let's dare. Okay, see what happens when we turn it on. Still getting overload. Oh well, let's see what the test does. Oh, let's see what the test does. What happened with that? Oh well. Not finding any errors now. That's good shit, isn't it? Let's measure the reference voltage. Reference voltage, test point 8. 10.02, 10.00, bloody good. And the negative 10.0, minus 10 volts. Good shit. I'm really glad it wasn't FETs, because some of them are hard, well, they're all hard to get, but some of them are dual FETs, and they're very hard to find anything that matches. Find any dual FET at all is going to cost 20 bucks minimum. Let's see if U13 pin 15 is now correct. Still 3.49. Okay, maybe that is normal. The 2.9 volts on U4 pin 7, still 2.9 also. So maybe there's something wrong still, but looking a whole lot better there. And test wise, right, we've got both 3455s together. Good one, repaired one, and we'll do a few crude tests. First, let's just turn them both on. Similar time to turn on, very similar readings, yellow and red. Oh no, I'm colourblind, but yeah, different coloured displays, different colour terminals here as well. Anyway, let's give them both a test. Same time, same, no errors, good. Put them both in DC volts, and we'll stick some volts in from this power supply and see if we get the same readings on both. So, yeah. This is about 7.9 according to that. They're pretty close, aren't they? Let's decrease the sample rate on both. Not flashing as often. Let's have high resolution. Increase the sample rate some more. They're pretty good. Especially this one hasn't got any of its shields on. Internal, all the covers. Okay, turn up the volts some more. Let's go to, there. 16.18. They're pretty close. Yeah. This power supply could be all over the shop too. Well, they're looking pretty good agreement there. Let's try some AC volts. Right, in ohm we're just doing 2 wire shorted out on the bottom one, so we get a low reading, and overload on the top one, so switch that to the top meter, and a low reading, very good. Now I won't bother trying 4 wire ohms, so we won't go to really low values. I'll just use a 47 ohm resistor, 47, and it looks pretty good. The bottom meter, this only shows Ks, so it's 0.047 K ohms. This doesn't have just ohms range. Let's try 6K8, 6.8K, and top meter. 6.8K. Beautiful. 330K. 330K. Not that close, is it? Let's see what the bottom one says. Is that within? These should be 1% resistors. So 330K, 1% should be 3.3K. More than that. Maybe the resistors are dodgy. Anyway, they both agreed pretty well. We'll try one more. That's as high as I've got. 1 meg. I suppose that is 1%, isn't it? Very close. Anyway, 1011.9K. Top meter. Not exactly the same, but close. Okay, I think that'll just about wrap it up for this. I'll put the covers on and try and do more extensive testing. I'm pretty happy about the results. Just one easy to replace part, not expensive. Good, yeah, I hope you enjoyed that. Of course, if you don't like this video, then why are you watching it? Catch you later.